Hello, friends. So Retrieval Augmented Generation, RAG, really established itself as one of the main techniques working with LLMs, seeing that the knowledge that is captured inside models, even the largest ones, isn't necessarily the knowledge we want to have available as part of the generation. Um, what we've seen happening quite a lot over the last year is a pattern where people are taking text, chopping it up, chunking it, indexing each chunk with embeddings, and then retrieving based on these embeddings in runtime to add these chunks to the context and generate text using that. That sometimes works really, really well, and in other cases, not so good. What definitely is becoming clear is that your RAG, your retrieval augmented generation, is only as good as your retrieval. Also, that your retrieval is only as good as your indexing. And so more and more effort has been going into indexing things in a way that allows us to do searches that are much more reliable and coherent. One really exciting development is the recent release of GraphRag by the Microsoft research team. GraphRag does something very special in indexing and retrieval. It uses large language models to read through the text and create from it a language graph. And with that language graph, we can then capture not just the original text, but the different relationships and entities and how they're connected to each other. And with that, create a context that is much more relevant, much more coherent, that can really include different details from parts of the text that can be further away, and where the indexing is not just reliant on embeddings, but on specific facts and entities that exist in the text and the relationships between them. So, what I'll do is take these two approaches to the test and see how they compare. This is a very, very simple test. There's a lot more than that that can be explored, but it's worth having a play with it. If you want, you can look at the notebook on GitHub or even clone it and play with it yourself. It's fairly simple, very straightforward, and give you some hints on how to use these both approaches and how they compare. So let's get started. We'll start by obviously installing a bunch of packages, quite a few, and then configuring our LLMs. We can use either OpenAI or Azure OpenAI, the same model deployed on Azure. This is very simple by creating a .env file and putting the values of the keys or endpoint there. What we'll do then is we'll take some text that we want to index and give it a go. So the text I pick is the Wikipedia article about the French Revolution. It's not huge. GraphRag is especially good for dealing with really large amounts of knowledge. In this case, it's just one article, but it's a fairly long article and quite complex with quite a lot of internal structure. So maybe it will already help us see what's going on there. We use here the Gina.ai reader. It's a really cool API from Gina.ai where they kind of take text and output it in a format that's very easy to digest for LLMs. Really fun to use. And as you can see, we got the text, title French Revolution, the source is Wikipedia, and it's obviously something that's been published very early in the life cycle of Wikipedia. Let's start by now chunking and indexing the text with embeddings in a more traditional retrieval augmented generation way. So what we'll do here, we'll use the markdown text splitter from LangChain. This is just a nice, convenient facility available as part of LangChain, among many others, for chunking text. And it's a little bit more aware of markdown structure, which exists in the text we just downloaded. We set here the chunk size, or the maximum chunk size, to be 300 characters. That means it will be at most 300 characters, but with awareness to Markdown, it might stop a little bit earlier. And overlap of 100 characters, which means that we'll sort of have a little bit from the previous chunk, then some more stuff that doesn't appear in the previous chunk. These are not necessarily the best parameters for chunking here. There's a lot of performance improvement that can be achieved just by playing with how you chunk and how you index, even for RAG. Given the size of the text and the size of the context, which we want to keep a bit limited here, even though we're using GPT-4, I think this might make sense. But just note that this might not be a completely fair comparison, because there's for sure a lot more improvement that can be achieved just by optimizing this kind of RAG. So we split the text to chunks, and we then send it to the OpenAI Embeddings API and use the text embedding free large to embed all of them, and then kind of create our own little index. We're not using here any kind of fancy vector index. It's not that much, and we can just do it all in memory. So we just store it all in a data frame with a column for text and column for embeddings. And you can see here we got 470 chunks, and they each come with the vector of embeddings. Let's look now at how we'll do the search with embeddings. So again, as I said, we're not using any special vector index or library. We'll just implement cosine similarity for comparing the embeddings of our query and the different chunks. So you can see the implementation here. It's really straightforward. We will then have a search function that takes a query and the maximum tokens we want to have in the context. In this case, we will limit the maximum tokens to 10,000 to really kind of see how we can the differences between using GraphRag and using just this very standard indexing with a limited context. Obviously, with GPT-4 having 120,000 token window, we could put almost the entire article in and it would maybe do something useful with it, but that wouldn't be that interesting for our case here. So if we look, we will create an embedding of our query. With that embedding, we'll then calculate similarity between the embedding for the query and each of the chunks. We'll sort by the chunks. We can sort of chop by number of top k, number of results we want to use. We might not even use it here, but that's how it would usually be done in these cases. And then look for results that are above a certain threshold of similarity. So again, not sure it would be necessary here, but below a certain level of similarity, it might not make sense to include something at all. And finally, we will count the number of tokens we have in each of the chunks that we selected using the tick token tokenizer from OpenAI, and only keep as many as we can afford with our budget for context window. And then we return a list of all the chunks that we want to include in our generation. So super simple implementation of vector embedding search. Now let's look at how we will generate using our embedding search. So one thing I try to do here is use the exact same prompt that is being used in GraphRag, so that when we do the comparison, is really only based on the difference in retrieval and not on some prompting hacks. And so you can see that we're importing this prompt from the GraphRag package. We define a response type, which is this is a feature of GraphRag that will kind of ape even in this simple embedding search. Set the max tokens for 10,000. We'll remove data from the result. The data stanzas are something that is being returned as part of the GraphRag generation prompt to include sources. This can be very useful, but it's not particularly interesting for our test here, so we just remove them from the text. And then we define this function ask embeddings with a query. So what it does is gets the results from our impromptu vector index using the embeddings. And it then invokes GPT-4o with the system prompts that we've taken directly from GraphRag, the response type we defined above, and with the query as the user message. Now let's look at GraphRag. So GraphRag is a really impressive piece of machinery. It can be used either as a command line or as packages you can import as modules in Python. In my opinion, the library in Python still is a bit difficult to use and not very well documented. The command line is pretty straightforward, so I decided in this comparison to just invoke the command line. What I'm doing here is so you can configure the command line with the YAML configuration files. I'm using the values we already have as part of the configuration we've loaded earlier to write this YAML. And then calling graphrag.index on the piece of text that we have, the French Revolution text. What you'll notice if you run it yourself is that whereas calculating the embedding for these 470 chunks is almost instantaneous, it takes like a couple of seconds, doing GraphRag indexing takes a lot of time and is also quite expensive, because what it does is it makes many different calls to the LLM, to GPT-4, reading the text and using it to extract entities and build connections between them and establish the graph. So that's a lot of upfront cost to get hopefully better results. Note though that this is a one-time expense. We're only doing it ahead of time. Later on, when we do the retrieval, it is also a bit more expensive, but not nearly as much as the indexing, which you'll see if you run yourself. It can take like a few minutes and quite a few calls. And now let's look at the query. So the query will again define a function askGraph, parallels directly the askEmbeddings function we've had, which takes a query. We will configure the maximum number of tokens for the context to be exactly the same, 10,000, and then invoke the command line of GraphRag for doing a global search. Global search meaning kind of bringing together information from the entire text. All right, so with that, let's start looking at how this works. We will now kind of try two different questions. The first one is timeline of the French Revolution. Should be possible, definitely information that exists in this article. And another one more specific, who was Robespierre and what was his role in the French Revolution? Oh dear. And we'll run both of these with embeddings and with GraphRag and look at the results. So looking at the results for Ask Embeddings with a timeline, it did return more or less the correct timeline. It also returned this outcomes impact. We didn't ask for that, which is quite interesting. I think this means that it got something in the chunks of text that were retrieved that were maybe not completely relevant for our question here. So this already gives us a hint. Looking at the result from AskGraph, yeah, this makes a lot more sense. This is exactly kind of what you'd expect for a nice timeline of the French Revolution, very accurate, summarized really nicely. So we can already see a bit of a difference here between the results of embeddings and GraphRag. In the next question, who was Robespierre? Again, we get some text that more or less makes sense, is correct. It definitely is coming from the original text when we use the embeddings. I'm not sure I would give it an A plus for an answer to the question, who was Robespierre and what was his role in the French Revolution. Looking at the result from GraphRag, I think that looks a lot better already. It clearly has read all the relevant text, summarized it very nicely. I would give this definitely a much better mark. But obviously, just kind of eyeballing the result and giving them our own assessment isn't a good enough evaluation. What we'd want in this case is to have some kind of systematic evaluation. And so let's have a go at that. What we're going to do here is super simple. Please don't mistake this for a really accurate systematic evaluation of a RAG system. This is really kind of back of the envelope version of it, but it works. We can use the LLM, GPT-4, to do some of the evaluation work for us. That is, look at the two questions, at the question and the two answers, and decide which one is better. Here it also helps that a subject like the French Revolution is obviously something GPT-4 actually knows very well, and so we'll be able to use its knowledge to do some of the assessment. So let's look at how we do that. We prepared here like 5 different questions. They are ranging from very specific to ones that require a bit more analysis. So we test different aspects, both kind of reaching into the text and finding a specific bit of information, but also reading the entire text and bringing things together. We will use my favorite way of interacting with LLMs, which is with Pedantic and Instructor, defining a format for the return in JSON, or first in Pedantic and then converting it to JSON. So we'll have here the best answer out of 2. It can be either answer 1 or answer 2. And we will have an explanation. This I find helps a little bit the LLM think why it's making a choice, right? The need to explain, I'm choosing answer 1 or answer 2 because. What comes now might look a little bit complicated, but it isn't really. Let's go over it. So we will go over each question, and we'll do each question 5 times because obviously LLMs are stochastic, not deterministic, and so it kind of helps to do something several times and then look at the different results we get. For each of these, we will generate an answer with AskGraph and with AskEmbedding. So we'll have answer graph and answer embeddings. And we will choose a random order for them just to make sure that the LLM is not biasing on which question comes first. I have no idea whether this is an issue, but I think it could be. So we'll make the extra effort to make sure that it will just be randomized. We will then call the LLM for our evaluation with the instructor wrapper and the eval answers response format. With the message, evaluate the 2 answers below based on accuracy and relevance to the question. Select the index of the best answer and explain why you made a choice. And then for the user message, we'll include a JSON dictionary object with the question and with a sorted list of answers. So again, remember, it's randomized. The first one may be graph or maybe embeddings, and we're keeping track of that. So after we run this, we will be able to get the result in as the evaluation object. We will add which is the best answer according to the LLM and the explanation. And we will then count for each question how many times was the graph sort of deemed to be the winner, the best answer, and how many times embeddings. And kind of record what was the question, which was the best answer, and how many times did the graph approach win, how many times the embedding approach win, and then the winner is the one that had the more wins. So we run that. It will take a while, right? Because calling the LLM with LangGraph, with GraphRag, it takes a little bit longer because of the retrieval method. But soon enough, we will have our answers. And so you can see the output here, truncated. It did all these questions. Graph definitely had the most wins in all the questions. In some cases, there were a few wins for embeddings, in other cases, none at all. And when we look at the result, out of 25 runs, right, 5 questions, 5 times, graph won 21 times and the embeddings won 4 times. So clearly a win for GraphRag here. Confirms our intuition from reading the results. Again, very simple evaluation, not really the level and quality of what you want to do to really evaluate a RAG system, but gives us already a hint that in GraphRag and in the graph approach in general, there's something very powerful. So where do we go from here? I think the biggest lesson here is that you can get a lot more performance, quality, accuracy by doing a lot more upfront, investing in indexing. It could be in the format of a graph, which is very useful, a very general approach for understanding a text and indexing in a way that keeps the semantics not just as embeddings, which are pretty opaque, but also the relationships between different entities. That's not the only approach. So I think more and more research into what we can do upfront to index our data in such a way that the retrieval can be much higher quality is definitely the way to go. GraphRag itself is impressive. It's very, very robust package. I didn't find it particularly convenient to use. I think an implementation that pays maybe a bit more attention to the needs of developers is maybe something that will still come, either from the GraphRag team or from other teams implementing a similar approach. But it's definitely usable. You can start playing with it now. So yeah, have fun. You can take this notebook, clone it from GitHub, and maybe try and play with different texts, different questions, different ways of evaluating the results, or just starting implementing your own retrieval augmented generation systems with more complex upfront indexing with a graph, maybe even with GraphRag. So until the next time, thank you and bye bye.